So that's me. Well, that's not a picture of me, but my name's Carlos Rodrigues. So I'm going to spend a bit of time talking about co-recursion, co-data, and combinatorial game theory. In the blurb for the talk, it says combinational game theory. My mistake, should be say combinatorial. So who am I? So I'm Portuguese South African, so that explains the name and the accent. I live here in Denver. I write Elixir for Blinker, which is a company that's trying to revolutionize the second-hand car financing and selling market. I have a dog named Molly, that's her in the bottom right. And I have interest in both chess and in rock climbing. And I'm not an academic, I'm just a normal Joe Schmo. Not that academics are normal Joe Schmoes, it's just that should hopefully give you an idea as to the timbre of my talk. So, why did I pick this topic? Well, I'm interested in FP. I've been interested in FP for about 2 years now. And I wanted to support LambdaConf. And when I was looking at the list of functional programming proficiencies that LambdaConf makes available, I saw Corecursion. And I thought, hey, that sounds cool. So I looked it up, learned a bit about it, and I was like, oh yeah, I'd love to talk about this. I saw that Codata was related. And when I looked at the two of them, I thought to myself, hey, you can totally use this to traverse a search space. And that search space could be a combinatorial game like chess. So I thought, boom, eureka moment, there we go. Having said that though, I think I should be in that unconf about how to write proposals, because I wrote 3 proposals. One was accepted, and of the 3, it was the most difficult one that I proposed. So just give everyone a moment. So just quickly about this talk. So I'm going to talk about, again, give an introduction to co-recursion, introduction to Codata, give you some examples, including a hand-wavy example of how to use it to do a mini-max tree with alpha-beta pruning. There's not going to be any generic abstract data types, despite what is said in the proposal. There just wasn't enough time. I'm not going to use any libraries other than Prelude, though there are good libraries out there for you to do these sort of things with. No proofs, nothing on bisimulation or co-induction, though that is extra reading that is very useful and very interesting. Well, I think it is very interesting. And most of my examples is going to be in plain code. So, the concepts I'm going to cover. Why do we need Codata and co-recursion? What is Codata? What is co-recursion? How to use co-recursion? And then just a little bit about the game theory, about minimax, alpha-beta pruning, and how to generate infinite game trees. So, why should you be in this talk? Why should we care about Codata and co-recursion? Well, with infinite lists, you can use, otherwise known as streams, you can use them to generate data in such a way that it helps the structuring of your programs. You can also use it to generate test data. You can use streams to model processes. And one of the examples that I'm going to give is that you use a stream to generate successive values of approximations that you can then feed to another consumer. What about infinite trees? You can use them to produce fractals, to produce chemical structures, to produce search spaces. There was even a way, I was looking for reference, I came across a reference you can use infinite trees in robotics, but I didn't have a good example, otherwise I would have put it up there. But also, you know, you can use it for bragging rights amongst your mates. And interview questions. If you bust out a co-recursion, you can tell them what a co-recursion is. I'm sure you're going to impress someone. I know it definitely impressed Blinker when I told him I was doing this talk. So, but infinite data, like how do you use infinite data? Surely, you know, it just goes on and on and on and on. How can this be useful? Well, a functional program is by definition a function because it's just a composition of other functions. So if you have a consuming function and a generating function, and the generating function is taking some input and generating just a list of successive outputs that's then being fed into the consumer, you the consumer is then in charge of how much data and what data it wants from the generating function. And how this is all made possible for us to use it is that lazy evaluation makes sure that there's going to be a strict synchronization between the generator and the consumer. The generator only starts when the consumer wants some input. It only runs for as long as the consumer needs input. And then it pauses or gets suspended until the consumer comes back and asks for more input. In the meantime, the consumer runs on that input, does what it's going to do, and then asks for the generator for more input. And then when the consumer is done, it terminates. And then when it terminates, the generator terminates too. So even though you have an infinite stream of data, that infinite stream of data is only being generated or in existence for as long as the consumer is in existence. So the implications of this: the generator is run as little as possible. It can be non-terminating. It can produce infinite data. And G just takes whatever it wants from that stream of data as much as it wants, and it is in control of the whole process. So a example here for the producer would be take 100. The take function is, by definition, a consumer. It's just going to take from the list, however long the list is, doesn't care how long it is, but it's just going to take from the list exactly what it needs to give you a finite answer. And then you can do an operation on that finite set. So I have been dodging defining Codata. So the best way that I could think of to define the Codata is to compare it with data. So both of them are a data type. Okay, fair enough. But Codata by definition is potentially infinite. Because it's potentially infinite, it's potentially non-terminating. And each of the successive values are usually generated in some form from the previous value. So if you take an example between a list and a stream being an infinite list, the list would have the finite data type. The stream would have the infinite codata type. And there's a little asterisk here to remind myself that, there's no such thing. Oops, I keep trying to highlight a word. There's no such thing as codata in Haskell. It is in Idris. So you can actually say whether a function is expecting infinite data or not. But having said that, you can still produce infinite data structures in Haskell. So the stream has no length, by definition, since it's infinite. It is either length 0 or infinite. It has no ending because it's infinite, and each value is the successor of the previous value. And you can consume the stream for as much as you want. Whereas for the list, once the list is finished, that's it. Your operation has to stop. Oh, and in the code example, you can see that with lists, you need to handle the edge case of the empty list. Whereas with streams, this will compile, but it will just never terminate. But you just have to deal with the one case. Conil, you don't need it. I threw it in there because on the research that I was doing, I thought it looked like it gave a more formal definition. But Conil would just be the absence of data in an infinite data type, which doesn't make sense to me either.
So in practice in Haskell, you would just use data and just note that it's actually codata?
Yeah, you just use data, stream A equals, and then stream A that it takes that has stream that is a product type of A and stream A.
Yeah, because if you had just the type that we're checking on the link for codata, you would have to handle conil case. Right?
Yes. So that does throw a little spanner in my explanation. Yes, sir.
If a stream does terminate, is it not a stream? Does it require that it's...
No, because streams can be productive or unproductive, and I'll touch on that a little later. So types are usually defined by their introduction rules or their elimination rules. So the elimination rule is how that data type is created, and the elimination rule is how that data type is then consumed. A couple of things is that the introduction rule will actually make an object of that type, whereas the elimination rule will break down an object of that type. And one thing that you will notice is that the constructor for the introduction rule is on the right-hand side of the equal side, whereas for the elimination it will usually be on the left. So if we keep comparing lists and streams, to create a list, you just apply the constructors. To eliminate a list, you use well-founded recursion. You look at the different cases, and you go from the larger case down to the terminating case. For a stream, to eliminate, you just use pattern matching. And to introduce it, you use corecursion. And when I was writing this slide, I thought that was funny, but that does lead me, though, into the next slide, which is, what is corecursion? So it's the dual of recursion. And for someone who doesn't have a mathematical background, I was like, what does dual mean? Is that like the evil twin? It's more like it's the brother of recursion, except one brother takes apart toasters and the other one puts the toasters back together and uses that toaster in another bigger toaster. Another example is Russian dolls. That's a very popular example when explaining recursion. You know, if you open up the bigger Russian doll, there's a smaller Russian doll inside, all the way down till you get to the smallest Russian doll. Corecursion goes the other way around. You use the first Russian doll to make a mold for the next Russian doll, to make a mold for the next Russian doll, and so on. So if you compare the two of them, recursion must terminate. It's analytical. It starts off with something large and reduces it down to something small. And it does that thanks to the properties of having a terminating base case and having a set of rules that can reduce any case down to that base case. And then thanks to Chris Allen, I had a little quick addition to this slide about Latin being run backwards, recursion being Latin for running backwards. Corecursion, on the other hand, starts at a seed and spirals further and further away from that seed. So it's synthetic. It creates more and more data. It has a starting base case, yes, but then it has a set of rules that goes from that base case to all the other base cases, not all the other following cases. And corecursion, as far as I can tell, doesn't mean anything in Latin, but co is a very popular thing to put in front of something that's the dual of something else. That's what I got from my non-mathematical musings. So if we were to look at an example, Fibonacci is very familiar to all of us. All right. So you have the base case of dealing what Fibonacci 0, Fibonacci 1, and then you have an equation that will, given any Fibonacci, given any integer, will figure out what the Fibonacci number is. That implementation, the performance is O(n) factorial, which is ridiculous. But with memorization, you can bring it down. But I want you to note that this is a method for solving, solving something. It is a function and it terminates. Whereas on the right-hand side, we say, hey, the seed is 0 and 1, and then we just use some function that takes that seed and adds to it. And you can see that I just say it's co-recursively defined by where I'm saying, hey, this thing is defined in terms of itself added to the tail of itself. So if you want to get the 12th and 12 assuming zero-based indexing, the 12th Fibonacci number is 144, and all you have to do is you just have to subscript the list at that position. But on top of that, you also get for free not exactly for free, but as part of the process, you can have you have a list of all the Fibonacci numbers. So if you want the first 13, or if you want to drop the first 12 and then get the next 13, you can play with that data structure.
I got a question.
Yes.
So how can you easily distinguish between the two? Because they both call themselves. How can you distinguish recursion from recursion?
So with regards to that, yes, they both have a recursive step, and in one of them I'm calling it the co-recursive step, and just because of the direction. Okay, so the direction of recursion will be from large to small, whereas the co-recursive step, I'm starting small and going large. So that would be the main way that I would tell the two apart. Yeah, the co-recursion starts at a base case and then just keeps going, whereas the recursion will reduce down to a base case and terminate. So those would be the defining characteristics, I would say. Does that help? Okay. So how does it achieve performance of ON? Because if you look at this, it's list within a list within a list. Okay. So again, lazy evaluation to the rescue. So what happens in the background with Haskell is that in order for something to be lazily evaluated, Haskell will take every little snippet of code, and not every snippet of code, like literals it won't, but everything else will put in a thunk, and will only evaluate that thunk when you access it. So if you have a tuple that has an equation and a value in it, and you say, hey, give me the second part of that tuple, it will return it says 12, it should say 4. Sorry. It'll return the number without doing any work. But as soon as you say, hey, what's in the first place, it will say, oh, okay, there's a thunk. Let me resolve this thunk and return an answer. And only then, in memory, does that thunk get evaluated into a literal. So, if we take this back to our co-recursive list, okay, you'll see that there's three operations. There's fibs, the construction of fibs, the construction of tail fibs, and then there's zip width, which takes the two of them and adds them together. So in memory, we'll have three references. One to a list that has the two seeds and then the thunk, and then the tail is going to be the one seed plus the thunk, and then the zip width is going to be the thunk altogether. But the magic trick in this is that, thanks to immutability, they're all references to the same list. So those three are sharing the same thunk. So when you call zip width, it's going to take it's going to take the head of the other two lists, add them together, add it to its head, and that is automatically going to update the other two lists because all three are using the same data structure in the background. So that's how you're going to end up with ON additions in ON space. So it's very quick. Like if you were to use that recursion function that I had before to get like the 50th Fibonacci number, it takes a while. It will slow down your computer. It takes like 5-15 minutes. Whereas with this list, it's really, really quick, nearly instantaneous. You can go up to 1,000 before noticing any slowdown at all, if any. Well, no, there is no slowdown. You'll just eventually run out of like integer space. So in this example here, like if I want the 6th Fibonacci number, the thunk will get expanded 5 times. All right. And then once that's happened, if I then go and I say, hey, what's the 4th Fibonacci number? That is already in this list, so no thunk operations occur, and Haskell will just return the answer in 01 time. So from here you can see a pattern already of how you create your own infinitely repeating corecursions. Okay, the identifier, a seed, and then the co-recursive step where it's literally just consing that identifier again. And if you want to repeat more than one value, you just specify those values like this, just using a sequence of the constructors, and then you do the co-recursive step again. Prelude already gives you functions that do this for you. In the first one, you can just say repeat 1, and it will give you the same infinite list. Or cycle 1, 2 will give you the same infinite list. But now, what if you want successively changing values? So natural numbers, you can do map, or you can use iterate, which is another function available in Prelude, where given a function, it will give you a list of that value, the initial value, plus that value with that function applied to it, and then that succeeding value with that function applied to it, and so forth. So to get the same list of natural numbers, you can just do nats equals iterate plus 1, 1. So what else can you do with infinite lists? Well, you can do operations on them to create more infinite lists, or you can combine them, or you can interleave them, anything your heart desires. But in the end, you're going to have an infinite list, because an operation over infinite list is going to be an infinite list. And at some point, you need to set up some sort of consumer that will say, hey, I only need this much. So just getting away from maths, if you had a game and you wanted to create one of those games where the player beats a boss monster and then a tougher boss monster comes out and a tougher boss monster comes out, this is how you go about doing it. So I just have a little data structure that models this monster, and then a function that, given the monster, will power it up a little bit. And then I just use iterate with that function and a beginning boss, and that'll generate an infinite stream of boss monsters for you to deploy against your player. So earlier there was the question about unproductive lists. So this is something that you should watch out for. So a productive list is one that just keeps going. So whatever is in the co-recursive step does not destroy what came before. Destroy is the wrong term, but does not exhaust what came before. So on the top I have a productive list. As you can see, the thunk, as it evaluates, just keeps spitting out 1. So it's going to be an infinite list that starts with 0 and a bunch of 1s. But the bottom list, the co-recursive step, exhausts any values almost immediately. So, and that will just, when the compiler goes to evaluate it, it just loops and will throw a runtime exception. In Haskell, no. In Idris, yes. And that is about as much as I can say. I'd love to go deeper into that, but I must admit that this is about a 3-month learning voyage for me. So I wish I had a deeper font of knowledge to go into.
In Haskell, if you abandon the direct recursive call in favor of exponent type, then you probably can.
Oh, yes? I would defer to your expertise, though, because...
Not my expertise, but other good talks.
Okay, good. So a less trivial example is if you wanted to figure out square roots using what's known as the Newton-Raphson, I think it's Raphson as opposed to Raphson, approximation. So it's just an equation that, given the number n being the square root, the number that you want to find the square roots of, you plug it into this function and you can get closer and closer approximations to the actual answer. So if you were to write this in imperative language, don't shout out which one it is. This is roughly how you'd write it. And you can see that the generation of the data, the approximations, is mixed into the function that does the testing, and the test is also mixed in. So, but the approximations themselves, if you look at them, each one of them is just going to be a list of successfully applied functions upon the initial value, whatever the initial value it is. So you can use that. You can use co-recursion to generate that for you. So I have the next function, which is just a function that is exactly that equation. And I just feed it into iterates to get an infinite list of approximations. And from the comments, you can see that it already starts to converge pretty quickly to the answer. then all you need to do is just write a consumer. So the consumer takes a list, looks at the first two values, and if they're within the tolerance, it returns that as an answer. Otherwise, it just keeps going, keeps consuming from the list until it finds a value that it finds that converged to the answer. And then the final definition would be just that where you take the consumer and you feed it the generator, and it'll spit out the answer for you, given whatever for whatever value of n. So separating the generator from the consuming logic means that now you can switch out the two of them as much as you want. They're just functions, so you can use either one, compose it with another function to get a useful operation. So here I took the within tolerance function, and I just converted it to be relative as opposed to absolute, so that it's better for really small numbers or really large numbers. And I didn't have to change much else. Okay, how am I in time? Oh, not too bad. So for my first conference talk, I'm not doing too badly. So how do you create your own infinite trees? So as before, you just have a seed and then a co-recursive step. You just repeat the same thing with regards to the trees. You have the seed node and then a function that will generate all the child nodes to that node. And here I've written it in such a way that it very much mirrors what iterate does. The data.tree library does provide a function called unfold tree that works very similar. So another example is, I came up with this on my own because I was like, what would I come up with? What infinite tree offhand would be really easy to do? So I thought, I read a comic once where the two people were asking, which one's deadly, a really big horse or an infinite army of really small horses. So I don't know, but now you can model it, okay? So assuming a player, you can generate a horse army, okay? And every level, every wave of horses has twice as many horses, each one with half the weight. Following the pattern that we had before, you just have a function that given a horse returns two horses of half the weight, and you feed that into iterate tree. And then data.tree has a really useful function called levels, which will actually give you the waves, the nodes at each depth. Then you can just feed that to attack the player with. Oh, and here's a quick screenshot of the functionalities that data.tree makes available for you to create an infinite tree. And there's a source code for unfold tree, which if you compare it to iterate tree, which we were using before, it's very similar. Okay, so that's it with regards to the concept. So we have Codata, co-recursion, why you want to use them, and how to use them. So let's delve a little bit into game theory. So combinatorial game theory, the goal is to look over some search space and to get an optimal set of actions from that search space. So you can assume that for example, the game of tic-tac-toe, the initial state would be an empty board that is a 3x3 grid. And then there are two players. Each of them has possible actions. One of them is placing an X in one of those open cells. The other one is placing an O in one of those open cells. And then R would be the function that, given the action and given the initial state, will generate the next state. And then U would be the utility function that would say, hey, is this a win, or is this position measurably better than the position before? So how you go about solving such a search space, because if you start off with staying with tic-tac-toe, if you start off with the initial grid, there's 9 possible actions. And then each one of those states, there's 8 possible actions for the second player. In each one of those states, 7. So in the end, you'll have a search space of 9 factorial. So what the method that you use to go over the search space that ensures that you have an optimal outcome is that you take the role of the max player. So when it's your move, you're trying to maximize the utility. And then the opponent is going to try and minimize the utility for you and maximize the utility for you, for themselves. So usually they'll be like represented by a negative value, whereas the max utility would be represented by a positive value. And then depending on whose turn it is, you eliminate, then you alternate turns and you pick either the maximum result or the minimum result. So the goal for max is to maximize the absolute worst case, because max will assume that min will play to the best of their abilities and make the best logical choice. So here's an example of a min-max tree, just assuming 2 moves, okay? And then the values on the leaves would be the utility. And here's some pseudocode that essentially just talks about what I had before. So if you have a leaf node, figure out the utility. If it's max's turn, maximize the outcome, the utility from the nodes below. If it's min's turn, minimize the utility from the nodes below. So to see that in action, assuming that it's min's turn, min is going to pick the leaves with the smallest values. And then when it's max's turn, max is going to, of those values, pick the largest. And so the best worst case outcome for max, given this tree, is to take this the action leading to this node, assuming that min will take the action leading to this node, and the best that max can do is 3. And I saw a hand.
The question is, given that you mentioned leaf nodes,
yes.
Is that just where you decide to stop traversing the infinite structure, or is that like actually?
So that's before actually introducing infinite structure. So at this point, I'm just talking about the concept of min-max. Okay. Any other questions? Okay. So a way that you could code this is on the left. You just have some function that, given some state, will generate all the possible states from that state, and then you can use that. And here I'm already using iterate tree to make an infinite tree. So you feed that moves and the initial state to iterate tree to generate an infinite tree of possible results. And then result would be the utility function. And then you just take turns maximizing or minimizing the result depending on whose turn it is, based on the depth into the tree. Problems with this, of course, is that if it's an infinite tree, so you'll never get to the leaf nodes to figure out what the utility is of that branch. Also, even if it's not an infinite tree, it's really these search spaces get really big, really quickly. So you still need to have some strategies to minimize the computational effort that you're gonna do to find the optimal answer. So a couple of those techniques are: you make sure that you only traverse up to a certain depth, and you use some heuristic that will tell you, with the information that you have so far, whether or not that's a good branch or not. The other thing is you can ignore portions that just don't affect the outcome at all. And that last is known as alpha-beta pruning. So if we were to change this code to have, instead of a result function that you can only run on the leaf nodes, you'd have a heuristic that you can run on that state, and will give you the best approximation as to the value or the strength, or the utility, of that position at that time. So, and then you'd use that when evaluating the result tree. But also you'd prune, in this case you're pruning to just 5 levels. You say, hey, generate only up to the 5th level and from this state, and then run the heuristic, and then give me the values. And then you'll use that smaller subtree to determine the optimal action sequence of actions.
Yes, you could flip the turn 5 to the front as well, and
Say it again.
You could split the order of pruning 5 and map for a heuristic and pruning last and might just sort you out.
Yes. No, because if
When you're turning it into the data, right? Not the data anymore.
yeah, when you're pruning it, you're turning it into data, and then you'd need to run the heuristic over that subtree to find out what the values are of the different branches. Sorry. Yes.
Because you will, when you prune, you're just pruning the results, but you won't have evaluated unless your heuristic sort of fully evaluates the tree, and instead of just evaluating one step at a time.
The heuristic. So the heuristic, or at least the example that I was working off of, the heuristic would only be able to give you a good idea of whether that sequence, that path of actions, was optimal or not by looking at the end state. Looking at the end state, looking at the leaf node. So you'd have to.
Yeah, I think you're right.
So you'd still have to have the tree in memory to be able to still have those still to get back from that optimal state to figure out what the actions were to get you to your current state.
Prune 5, but 5 is only how far forward you think you look ahead to tell you which one's the best.
It's gonna just stop. So if I have an infinite tree, it's just gonna go 5 levels down, cut it off, and hope that it can figure out from that subtree, from that smaller tree, whether hopefully there's enough information there for the heuristic to give you the true value.
You won't keep building a 5 once you make a decision, you go down the next one, you go 5 forward, no? Just doesn't work.
Just as once.
Excuse me.
Yes.
On the second definition of your prune function, is there a bit that's missing? It seems like that would be a syntax error on the right side.
Oh, there is a parenthesis missing. Yes. Is that what you're referring to?
Yeah.
Okay. Yes. I can definitely fix that. Anything else? All right. So alpha beta pruning is you have a look at the possible outcomes and you say, hey, do I need to evaluate any more branches? So in this example here, your algorithm would totally evaluate the right-hand branch, okay? But then from the right-hand branch, it knows, hey, okay, from this branch, the best that I can do is going to be a 3, all right? So as soon as it starts to look at the other subtree, as soon as it hits a value that's less than the 3, since we're going to maximize the results of this equation, the fact that this is a 2 doesn't matter because we're going to pick this 3 at the end. So, but since we know that there's a value smaller than our current maximum, we don't need to evaluate any of that because we're going to assume that minimum is going to pick the option that is the least valuable to you. So if these values are 1 or 0, doesn't matter because we're going to pick this. We're going to pick this branch. And if these values are higher than 2, like 4 or 5, doesn't matter because min is not going to pick them. So we don't have to look any further. This one, though, we just kept going because for none of these values, not until the end, do we actually get to a value that's less than the maximum that we determined at the beginning. So this equation will then essentially become maximum of 3, minimum 2, and then 2. And we don't care what those 2 values are. And in the end, we don't care what the middle value is. That should be a 2. My apologies. And then, so the answer, whether or not we evaluated these 2 branches, was going to be 3. So that's alpha beta pruning, is being able to make these decisions to say, hey, there's no need to go down this path, no need to go down this path. So what will end up happening is the entire subtrees will not be expanded.
A theoretical question.
Yes.
These trees are built as Codata, right?
Mm-hmm.
So it's just like all possible moves branching out forever.
Mm-hmm.
My question is, we're talking about the leaves. So like the 3 at the bottom, is that representative of like the state at that moment
Well,
of the world?
so so here, where this is obviously a finite tree, but how we'd be able to do this sort of thing would be thanks to the pruning, because before we do this step, we're going to prune to a certain length so that we change the Codata structure essentially into data that will actually terminate at a level.
My question is, if the 3 is something that's just there at that moment, or if it's generated by co-recursion, so it's taking into account the node above it and the node above that. So, because I'll go to the endpoint. I can imagine getting to a state in the game and being able to look at the board and say, is this right? Or is this good? But I could also imagine something where you jump pieces and you collect them at one stage. So really, I've just added 5 pieces, and as I take each move, I'm adding to a pot. So instead of the state of the, well, I guess you can do the state of the board is how many pieces are remaining. But I'm trying to do something where you're gathering as you go, so really the whole path is the answer, not the endpoint.
Well, the whole path will be the answer, but also in that situation, the state will be the board, but also the pot. You know, because like especially if one of the victory conditions of the game is capturing more pieces, then there would be a score that you'd use in the heuristic to tell you whether or not. Apologies. There'd be part of the heuristic that would tell you whether or not the that position or that board or that set of moves was beneficial to you.
Okay, so as part of the co-recursion, you would be bringing the collection of pieces down.
Yeah. So the
I have collected 20 pieces.
yeah. So yes, there'd be part of the state that you generate in the co-recursion. And here's just a bunch of code. But essentially, the maximum and minimum functions from before now have little extensions that will emit branches as soon as it finds, it will emit branches if it finds a minimum or a maximum, depending on which effort you're doing, that is less advantageous than the maximum or the minimum that you have up to that point. And I can make all of this code available. I'm going to make the slides available as soon as this talk is over. I'm just going to Slack out a link to a PDF. I'll also give it to the volunteers at LambdaConf so that they can make it available to you guys. And then I can also Slack out links to the source code. But quite a bit of this is because, like any great man, you know, my efforts are built on the hard work of other people. So in the sources, you can see where I got this code. So that's it. So we covered all the concepts. We covered minimax and alpha beta pruning, and the trees being generated co-recursively. And that's it for my talk. Thank you. So the sources that I had are all of these. Some are online. Some are just like internet articles. Like you'll see a Stack Overflow link there. That was very useful with regards to explaining the thunk. One of the things I didn't get to talk about was how you can use co-recursion to model a process where you can use a co-recursive function to map out or traverse a finite, not finite, a deterministic state machine or non-deterministic state machine. There you go. So that was very useful reading, and that you can find in the Haskell wrote logic book. The minimax idea came from John Hughes, and the code came from Michael Maloney. Oops, not Michael Maloney, Benjamin F. Jones. Okay. All right, thank you very much. Any questions? Nope. All right.
Did you build your own trust team using this?
No, I started to, but then I was just, shall we say, intimidated by what needs to go into it, because even though this gets you a lot of quite a way down the road. Writing the evaluating function and pruning what states you create. You need an opening book and a lot more heuristics than what I was ready to delve into. So. Okay. Thank you.